Assalamualaikum and good day. We are from Group 5 in Section 1. We will presenting about our PBL2 activity, which is digital modulation and transmission. So let me introduce our group members. First, Fatih Farhana binti Muhammad Nur Afaf Hanani binti Zakaria, Muhammad Harith Akmal bin Ahmad Badruddin, Nur Shafura binti Muhammad Muzakir, and Muhammad Nur Firdaus bin Ahmad Zaki. Introduction. Digital modulation is a system that produces information regarding capacity, high data security, and also provides great quality communication with quick system availability. PCM is a digital program that transmits analog data. PCM encoder, or we know as pulse code modulation, process consists of sampling, quantization, and encoding. Sampling is a process that converts continuous time signal into the discrete signal. Quantization is a sequence of pulses with amplitudes that fall between the signal's highest and lowest amplitudes, while encoder is a process that digitizes the analog signal. So I will pass to my group member to explain more.
Assalamualaikum warahmatullahi wabarakatuh. My name Fatih Farhana binti Muhammad Nur. My metric number is AE190068. So now I will explain the filler table and fishbone diagram. So for the first fact, which is pulse code modulation, the ideas of analog signal will be converted into a digital signal which is binary form with the help of ADC, or we can call as analog to digital conversion. Pulse code modulation also requires to go through sampling, quantization, and encoding process in analog to digital conversion. So for the learning issues, learn the conversion process where it will be starting from analog information signal to digital information signal. Next, learn to differentiate the type of sampling technique, quantization, and finding bit rate, bandwidth, and others in encoding process. So for the action plan, we learn from the research papers, lecture notes, and websites. Okay. For the next facts, high frequency component must use low pass filter or anti-aliasing filter before sampling process. So we can say that the value of high frequency component is above Nyquist frequency, which can lead to aliasing error. Also, to achieve accurate sample signals constructions, the value of analog input must be below Nyquist frequency, which is Fs is more or equal to 2 FM. So, for the learning issue, study on how to ensure the value must be below Nyquist frequency to avoid aliasing error occur during the sampling process. So for the action plan, we improve our understanding by studying from websites and YouTube platform. So for the third fact, which is higher number of bits leads to an increasing in level numbers. We can say that the higher the quantized level, the lower the quantization noise power. Thus, better and secure data transmission can be produced. Next, higher bit rate possible to achieve the better quality. So for the learning issue, discover the characteristic of PCM and its advantages. So for the action plan, we refer to the additional notes from research papers and websites. So for the next fact, modulated signal equation will generate the important values needed in PCM. So for the ideas, the value of sampling frequency is different in every scenario, whether identical, less than or more than the value. Sampling interval obtained from sampling frequency. Lastly, angular frequency from modulating signal determine the modulating frequency. So the remaining issues is to learn on how to calculate the sampling frequency, sampling interval, and modulating frequency. Our action plan is to refer to its theory formulas from lecture notes and websites to gain the values needed for the PCM in simulation software. So for the last fact, PCM code was determined by analog sample voltage. So for the ideas, with the help of quantization range from 3-bit PCM code table, PCM code will then be developed into a complete binary form. So I also can say that every value will have its own PCM code. So for the learning issue, we study on how to determine the PCM code by referring to the table of 3-bit PCM code. So for the action plan, we refer to the lecture notes for a better understanding in completing this group assignment. So that's all for the filler table. So now we will move to the fishbone diagram. Okay, now for the fishbone diagram, our effect is failure in false code modulation. So what are the causes to this effect? So there are 4 causes here, which are flexible step size, low bandwidth value, faulty in encoding and decoding, and also aliasing error occur during the conversion of analog to digital. Okay, now we will go to the first cause, which is flexible step size. So what are another causes to these causes, which is change in number of bits and also non-uniform signal to quantization ratio. So for the low bandwidth value, we can say that it is affected by the low bit rate, which is happen from the low sampling rate and low number of bits per sample. And another point is undesired waveform fast shape. So for the third causes, which is faulty in encoding and decoding, we can say that it is caused by the quantization error occur, which is the linear encoding is used and the maximum attenuation in the process. So for last point, which is aliasing error occur during the conversion of analog to digital, it is affected by the component signal above request frequency and incorrect frequency and or amplitude, which happens from the too low sampling frequency. So I think that's all for the fishbone diagram. So that's all from me. Thank you.
Assalamualaikum, my name is Nur Afaf Hanani binti Zakaria and I will present part A. So this is the equation that have been given in the question, which is mt equals to 5 sine 2 pi 100t. So from the equation, we can find out that the modulating frequency equals to 100 Hz and the amplitude is equals to 5. So part A is divided into 2 parts, which is scenario 1 and scenario 2. So the sampling for MT in part A is the minimum required according to the Nyquist rate. So for the scenario 1, the sampling frequency Fs is equals to 2 Fm. So using the value of Fm equals to 100 Hz, we can find the value of Fs equals to 200 Hz and the n-bit encoded PCM data is equals to 4 bit. So from the value, we can find the value of period t using the equation of 1 over frequency, which is 1 over 200. So this is the block diagram for the encoding and decoding. So first I will show the value in the sampling pulse signal. So the value in sampling pulse signal is amplitude equals to 5 and the period is equals to 1/200. Next, the value in modulating signal, amplitude is equals to 5 and the frequency is 100 Hz. For the sample and hold block, we let the initial condition equals to 0. For the encoder block, the peak is 5 and the bit is 4 bit and we put the output type as signed integer. For the integer to bit converter, the number of bit per integer is 4. And for the bit to integer converter, the number of bit per integer is set to 4 too. Same as the encoder, the decoder peak is 5 and the bit is 4. And the sample and hold initial condition is 0. And for the analog filter, the filter order is 4 and the passband edge frequency is 100, which is same as the modulating signal. So we run it. So this is the output at the 4-bit encoded PCM display. So this is the output for the 4-bit encoded PCM display. We have sampling pulse signal, we have modulating signal. This is the non-uniform quantized signal. This is the encoded quantized signal, and this is the signal after the integer to bit converter. So we can see that the sampling pulse signal is in square waveform and the amplitude for the sampling pulse signal is equal to 5, which validates the amplitude value that we put earlier. So the modulating signal is in sine waveform and the amplitude value is also equals to 5 and the non-uniform quantized signal is like this. The maximum and minimum peak value is equals to 5 and this is the encoded signal. We can see that the value of the maximum and minimum peak for this encoded signal increases after the uniform encoder block. So lastly, this is the signals for the integer to bit converter. So there are 4 signals over here, which the yellow one is for the integer to bit converter 1, the blue is for the second, the red is for the third, and the green is for the fourth. Next, this is the last signal for the oscilloscope. So this is the output signal at the oscilloscope. This is the modulating signal and the blue one is for the resultant recovered modulating signal. So we can see that for the modulating signal, the maximum and minimum peak value is equals to 5, which validates the value that we put in the block diagram. And for the resultant recovered signal, we can see that the maximum and minimum value decrease. So the maximum value is 3 3.2, and 3, while the minimum value is minus 3.7, minus 3.8. So from this signal, we can see that the amplitude value decrease after the encoding and decoding process. Next, I will show for the scenario 2. So for the scenario 2, the sampling frequency is the same, which is 200 Hz, and the n-bit encoded PCM data is equals to 8. So I will change the value in the block. So the value that we have to change is the value of n-bit. So we need to change over here 4 to 8. Number of bit per integer equals to 8. Over here also 8. And lastly over here is also 8. So we can run it. So here is the output signals for the 4-bit encoded PCM display. So we can see this is the sampling pulse signal which is in square wave, and the amplitude is equals to 5, which validates the value of amplitude that we put in the block. So this is the modulating signal, and the maximum and minimum peak value is equals to 5. And this is the non-uniform quantization signal. And we can see that the maximum and minimum value is equals to 5 too. And this is the encoded signal. So from here, we can see that the maximum and minimum peak value for the encoded signal that passes through the sample and hold block and the encoder block increase. So the maximum value is 127. And the minimum value for the quantized encoded signal is minus 128. So lastly, this is the signal that pass through the integer to bit converter. Lastly, this is the signals for the oscilloscope. So this is the modulating signal, and we can see that the maximum and minimum amplitude value is equals to 5. And this is the resultant recovered modulating signal that we need to find. So we can see the maximum and minimum value decrease from the original value. So here, the maximum value is 3.5. And the minimum value is minus 3.5. So in conclusion, the n-bit value of 4 is not as accurate as 8 bits because the bandwidth and the quantization level of 8 bits are larger than 4 bits. In order to get more likely of the original signal, the value of sampling frequency and the quantization level need to be higher so that the bandwidth will increase. In part A, the minimum sampling required according to the Nyquist rate were used to get the resultant recovered modulating signal. Based on the signals generated in scenario 2, we can see that its modulating signal its resultant recovered modulating signal is more accurate than scenario 1. It is because the number of bits used in the blocks of scenario 2 is higher than scenario 1. So the results produced by 8 bits showed more accurate signals than 4 bits. And that's all from me.
Okay, Assalamualaikum and hello. My name Muhammad Fidau bin Ahmad Zaki. Matric number CE190052. Okay, so first of all, I would like to seek for apologize because I did not attach the face cam. This is because my webcam has already broken last week. I already purchased a new one, but it not yet arrived. I purchased in the Shopee. It takes so long time. Okay, so for the PBL2, my part is doing the part B and part C. Okay, so for the part B, we will require to do sampling for MT, which is more than required frequency, which is FS is greater than 2 FM, and we need to encode for the 4 bit and 8 bit. Okay, so I need to do this fast because the OBS is hang. I don't know why. So this is for the modulation process. We can see the sine wave, the sampling plus turn the signal into this. And for the 4 bit encode display, and for the oscilloscope. Okay, so the blue one is the output. And for the part B for 8 bit, okay, so here we need to change the integer for 8 and the encoder 8, the bits is 8, and here for the 8 bit encode PCM display. So when I run the simulation, so this is the modulation process for the part B 8 bit, and this is the 8 bit encode PCM display when it's 1 2 3 4 5 6 7 8. Okay, so we move to the part C. Okay, so this is the part C when I run the simulation. Okay, so this is the modulation process. Okay, so for the part C, we need to do the sampling, which is Fs is lower than 2 FM. So I use 50 Hz, and for the part B I use 300 Hz because the FM is 100 Hz. Okay, so this for the oscilloscope, which the output is not okay, so as we can see here, the what we call it, the signal is the sampling pulse is turned in. We can see how the sampling pulse signal turn into analog signal into a multi-level pump PAM, which is then undergoing quantization through the encoder. This is the encoder. So with the sampling pulse 50 Hz, the modulated signal is sampled in 2 complete cycles. Okay, so that's all from me. Thank you.
Assalamualaikum, my name is Ahmad Haris Akmal, number CE200145, and now I'm going to explain about the PBL2 design for ECS subject, which is for noise and digital modulation and transmission. So my part is for me to figure out part D, which is with initial setting part B, I remain. What will happen to recovered message MT if amplitude of MT is changed to VM is equal to 15 volt and VM is equal to 0.5 watt. So in part D, we are required to use the initial setting of part B, which is as shown before. So with more than required according to Nyquist, with the sampling frequency of Fs more than 2 FM. And decoded to 4 and 8 bits PCM data respectively, and the results are already stated before. Now in part D, by using the initial setting, we set the VM to the 2 different value, which is 15 to 0.5 volts. So let me show you the. Okay, this is my design of the block diagram of the modulation. So everything is set, the parameters is set correctly as shown, and the encoder is set to 5 peaks 8 bits, and uniform decoder is also set to 5 peaks 8 bits. For this is the default value from part B. So now we're going to change it to 15 volt, which is from the sine wave. The amplitude should be changed to 15 volt. Okay, hit OK. So I will run the this is the output from before. Okay, and also this is 5 volt output of the from the oscilloscope. So now after we run from 15 volts, we can check again. So there's a change in the FM, and also there's a change in the oscilloscope. So yeah, okay, from the signal output we can see that the high level signal, which is 15 volt, is having problem quantizing the signal, resulting in some quantization steps being wasted, which is, as you can see, this caused the output signal to be out of shape from the signal input signal. So moving on to the 0.5. Okay, let me change it to 0.5. Hit OK and run it. Okay, now okay, there's the FM change, the PCM also changed. Now, okay, now you can see for the low level signal, according to the graph, VM is equal to 0.5. Seems to have a less problem dealing with the quantization, which results in a similar output signal compared to the previous one. So that is from this question from the VM. Now I'm going to move on to this question, which is, what would you suggest to make sure the resultant recovered signal MT is similar to modeling signal MT? Discuss to prove your finding. Okay, now I'm going to show you how to do the recovered one. So firstly, to make sure that the resultant recovered signal MT is the same or similar to the modeling signal MT, we we will adjust the modeling signal MT of the peak signal. So here we adjust it from the encoder, which is, we change it to, firstly we need to do 15, hit apply, and also the decoder we need to change 15, apply. So for now we can hit run. Okay, for both encoder, from, let's see the signal. No, let's see the oscilloscope. Okay, now, okay, from the signal that we have seen right now, okay, the output signal and the results from here we have become similar to the input signal. So we can see that the quantization peak or interval voltage range is important to allow amplitude modulating in the certain ranges, and by adjusting both peak values in encoder and decoder, so that we were able to achieve a good digital transmission. So it is the same as 0.5. We just change it to 0.5, 0.5. Okay, 0.5. We click run. It's similar to the, yes, as shown, it is similar. So after we change the peak and the voltage interval, we achieve a good digital transmission. That is all from me. Thank you.